let's have a quick review of what we have discussed in our last class. In the last class, I hope we were trying to talk about stresses in the soil. How do we calculate the stress in the soil? And in the process of discussing about that stresses in the soil, we started talking about how to calculate the stress in the soil or in the ground at any particular depth, irrespective of the condition of the soil, whether the soil is dry, whether the soil is saturated or partially saturated, whatever. But in the case when there is no flow happening through the soil, okay, I repeat, when there is no seepage happening through the soil, we have seen how to calculate the stresses in the ground. And when we started talking about the stresses, we have certainly discussed about three varieties of stresses. One is total stress, other is pore water pressure, third one is your effective stress. And all that what I am trying to talk about, either your total stress or your effective stress are nothing but are in the vertical direction. But when we discuss about pore water pressure, we don't particularly say pore water pressure in the vertical direction or in the horizontal direction. The reason is pore water pressure, whatever gets developed in the pore space is uniform in all the direction. Okay, so that's the reason why we say the pore water pressure that is being calculated is same in all the directions whenever your soil in which you are trying to calculate that pore water pressure is fully saturated. In the case of partially saturated soil, we don't talk about your pore water pressure, which is uniform inside your pore space. Okay, so now let's move on with the next continuation topic, that is stresses in the same saturated soil in case if you have a seepage happening. Earlier we have talked about when there is no seepage happening, though the soil is saturated, but we didn't had any effect of seepage happening through the soil. And now in today's class, we are trying to see the case how to calculate the stresses in the saturated soil when there is a seepage happening. What is this seepage? Seepage is nothing but the flow happening through your cross section of the soil sample. Now, when does the flow happen? Whenever there is a total head difference between the so-called upstream to that of your downstream. So which is called as upstream, which is called as downstream, already we have discussed about it. So when there is a total head difference which is causing that flow, then we see the seepage happening through that particular soil. Okay, so the flow, whatever I am trying to discuss about, is happening in the downward direction. Now, why is this particular flow happening in the downward direction? Because let's say at the bottom you have a wall. Okay, so once the particular wall what you are referring to is open, then the flow direction what you are going to be looking at here is going to be in the downward direction, because the total head referring to that of the point. Okay, let's say the point A, here is your point A. Now the total head, when I try to calculate at this particular point A, the total head is nothing but elevation head plus pressure head. If I take this bottom of the soil sample as my reference datum, okay, if this is considered as my datum, so with respect to the chosen datum, how much is my total head with respect to point A? So the total head corresponding to the point A position. So if I just start writing down, total head corresponding to point A is nothing but pressure head corresponding to point A plus elevation head corresponding to point A. Now, elevation head is nothing but from the chosen datum at what height your point A is existing. So at what height my point A is existing, elevation head what I try to calculate comes out to be from the chosen datum, point A is at a height of h2 meters. And the pressure head, if I want to calculate how much is the pressure head existing at point A, then what I can understand is try to see from point A at what height your water table is existing, or in the other way, from the water table position, from the topmost water surface position, at what depth your point A is existing. So point A is existing at a height of h1 from the top surface of water. So my pressure head at point A is nothing but h1. Elevation head corresponding to point A is nothing but h2 from the chosen datum. Then my total head what I am trying to calculate is nothing but pressure head plus elevation head, where pressure head is h1 and elevation head is h2. So the total head at point A is nothing but h1 plus h2. So that is what I can write down. Your so-called total head what I am trying to calculate at point A is nothing but h1 is your pressure head and h2 is what is your elevation head. And next, to understand what is my total head at point B, because when there is a total head difference between upstream to downstream, so-called point A to point B, then only I can understand the flow is happening from the soil or through the soil from point A to point B. Okay, so in the process, when I'm trying to understand what is my total head at point B, So at point B. So similarly, the elevation head corresponding to point B plus pressure head corresponding to point B. The elevation head corresponding to point B. Where is the point B? Point B is existing at the datum position. So automatically this so-called elevation head, what I am trying to refer to, is nothing but 0. And the pressure head, if I am trying to calculate, okay. So if I am trying to insert a standpipe, here, as we are saying, the valve is opened. Once the valve is opened, what is going to happen is the water tries to flow through that particular valve. And once the water tries to flow through the valve, automatically the soil, what you are looking at, will have the flow happening from the top to the bottom, because the valve is there at the bottom. So automatically, because the water storage is on the top and the valve is at the bottom, so automatically the water tries to flow in the downward direction. In case if the water available on the downstream is at a higher elevation, then that of the water available on, let's say that water distribution, whatever is available corresponding to point B, is having a height of water storage which is relatively higher than that of the water storage available at the point A, then automatically the flow will happen through your soil sample in the upward direction. And that's how we try to say your flow is going to be happening from what is called as your upstream to downstream. In this particular case, the upstream is nothing but your point A, the downstream is nothing but your point B. So that's how we understand the flow happens through your soil sample. If the valve is not opened, I repeat, if the valve is not opened, then once we start calculating what is my pressure head at this point B, so the pressure head, whatever we try to calculate at point B, so it comes out to be in the same way. Once there is no flow happening, automatically how much will be the pressure head corresponding to point B? I'll be looking at the top surface of your water table. So from the top surface of water table, at what depth your point B is existing? Automatically it is H1 plus H2. So my pressure head at point B is nothing but H1 plus H2, and elevation head was 0. So automatically when I calculated my total head at point A is, it's nothing but H1 plus H2. And the total head that I am calculating at point B also comes out to be H1 plus H2. Automatically, which indicates there is no flow happening from point A to point B. This is all going to happen only when the valve is closed. Once the valve is open, then there is a pressure release happening at point B. That's your pressure head, whatever you are trying to talk about, is getting released. Why is it getting released? Because the water particle which is available at point B position can easily move towards your drainage path, and it comes out. So that's how your so-called total head difference between point A to point B starts decreasing. And what we see is, let's say for example, if the total head available at point A is something, and the total head available at point B is something, and the total head difference between point A to point B is what is referred here as your H. Okay, so that's so-called H, what is indicated here is referring you what is called as your total head difference between upstream to that of your downstream. Because of that small H difference, which we are calling it as your total head difference between upstream and downstream, the flow is happening through your soil sample. Now, because of that flow happening through your soil sample from point A to point B, which I am calling it as your downward seepage. Okay, so because of that flow happening through the soil sample from point A to point B, if I am required to calculate how much stresses are getting developed in the soil, now whether the stresses, so-called effective stress, which I am going to be talking about in the soil, will it increase? Will it decrease because of this seepage happening through the soil? Let us try to understand. If it is decreasing, will there be any issue? If it is increasing, will there be any issue? If the effective strength of the soil increases, there is no problem. But if the effective strength, when I say strength, it's nothing but the stress in turn, I am referring in terms of stress. Okay. So if the effective stress increases, not a problem, because the strength between solid particle to solid particle in terms of its contact is increasing. But when the effective stress developed in the soil decreases, then automatically this so-called particle to particle resistance is decreasing, because of which the strength of the soil decreases, and automatically you have certain possibility of coming across with a failure in your soil or any structure that is being constructed on that particular soil. So we have to be little careful in understanding how the flow happens through your soil sample. Because of that direction of flow, whether the stresses in the soil are increasing or decreasing, or are they remaining same, depending on that, we will be able to understand will that seepage what is taking place through the soil is going to cause any particular issue to your structure existing in that particular soil. Okay. So let us quickly go through how to calculate the stresses at different points, what you are trying to refer to, maybe at point A or point B or point C, if you are interested in looking at. Okay, so we'll try to see how to calculate the stresses at different points in the soil sample, not just only at the top and bottom, at any other point also within the soil sample. If stresses are to be calculated, we can try to see that. Now, if I start looking at how to calculate the stresses at point A, so that is nothing but the total stress, pore water pressure, and your subsequent effective stress. So if I want to calculate all these three stresses, so how do we calculate total stress? In general, total stress is nothing but at any point, if you want to calculate the total stress, it's the effect of the mass of the substance which is existing over and above that particular point is what is going to give you what is called as your total stress. Now, if I look at your point A, so at point A, with reference to the position of point A, here is my position of point A. What do I have above this point A position? It's nothing but it is simply water. So because of the weight of the water, or because of the mass of the water existing about point A, I am going to see the effect of stress, so-called total stress at point A. So how much is going to be my total stress at point A? Unit weight of water is nothing but gamma W, and over what height the water is existing above your point A, it's nothing but H1. So automatically your so-called total stress, which I am trying to calculate, okay, so the total stress is nothing but unit weight of water is gamma W into the corresponding height of water what is existing above the point A is nothing but H1. So that gives you what is called as your total stress at point A. Now, once I understand what is the total stress at point A, then let's move ahead in understanding how to calculate your pore water pressure corresponding to the position of point A. Now, if I look at the pore water pressure, what is existing corresponding to the position of point A, so how much is my pore water pressure corresponding to the position of point A? So if I just want to understand how much is the pore water pressure corresponding to the position of point A, so pore water pressure at point A is nothing but what is the rise of water level in the standpipe that is inserted with respect to the position of point A. So water in that particular standpipe has raised up to this level. So it indicates that the pressure head corresponding to point A is nothing but it is same H1 meters. And once the H1 meter is the pressure head at point A, then automatically the pore water pressure is nothing but unit weight of water into corresponding pressure head existing at point A. Okay, so my unit weight of water is gamma W and the pressure head is H1. So automatically my pore water pressure corresponding to point A is nothing but gamma W into H1 is what I'll be getting as your pore water pressure. So once we get your total stress at point A and pore water pressure at point A, automatically effective stress, which we call it as your total stress at A and pore water pressure at A, is the difference between total stress and pore water pressure, which is gamma W into H1 minus gamma W into H1, which gives you that effective stress, whatever you are calculating at point A, is nothing but it is equal to 0. In the last class, I have told total stress is nothing but the stress that is being carried by the solid particles as well as the water particles existing in the soil medium. That's nothing but total stress. Once we say it's a stress carried by the complete soil. Okay. Now, when you look at pore water pressure, it's nothing but the stress carried by only the water particle existing in the pore space. And effective stress is nothing but it is the stress carried by the solid particles. Now, if you look at the point A, do I have any solid particles existing over and above the position of point A in this region? I don't have any solid particle. Soil solids are not there. Only water particles are there. As soil solids are not there, automatically the stresses carried by so-called non-existing soil solids is obviously 0. That is what I am getting from this expression. The so-called effective stress that you have calculated, the expression says the same. That effective stress at point A is automatically coming out to be 0. Because I don't have any solid particles existing over and above your point A to take some loading onto it. Next, if I want to calculate how much is my total stress at point A and how much is my pore water pressure, stresses at point B, if I want to calculate, then I'll be looking at in calculating how much is my total stress at point B, pore water pressure at point B, and automatically the effective stress corresponding to the position of point B. Now, if I want to calculate what is my total stress at point B, pore water pressure at point B. So now let me try to understand what will be my total stress at point B, your pore water pressure at point B, in order to calculate your effective stress at point B. Now, if I want to calculate what is my total stress at point B, total stress at point B is nothing but it is equal to So when I want to calculate the total stress at point B, total stress is all because of the material which is there over and above that particular point. Okay. So what is that material which is there over and above that particular point B? To a height of H2, I have soil. Above that, to a height of H1, I have water body. Okay. So the total stress at point B is nothing but it is equal to, because of the water body, the some stress would be developed. So that's nothing but unit weight of water body into the corresponding height of that water body is going to give you, due to the effect of water body, how much is the stress at point B, and then additionally due to the effect of soil strata, how much is your stress developed at point B. That is your total stress. So once I say due to the soil, let's say the unit weight of the soil is gamma, as the soil is in a saturated state, so I'll be writing the unit weight of that soil as saturated unit weight of the soil. And once we write down the saturated unit weight, what is the height of that soil strata? That's nothing but it is H2. Okay, so gamma W into H1 plus gamma Sach into H2 gives you what is your total stress at point B position. Once we understand what is your total stress at point B position, next let us try to see how much is my pore water pressure corresponding to the position of point B. What is my pore water pressure? How much is the pore water pressure corresponding to the position of point B? So if I want to calculate the pore water pressure, I should understand what is the pressure head corresponding to point B. Because pore water pressure at any point is nothing but unit weight of water into the corresponding pressure head. So at point B, how much is the pressure head that is existing? So if I want to understand, you can look at the standpipe which is inserted with respect to the position of point B. Okay, so this is the position of point B, and with respect to this position where a standpipe is being inserted at this particular depth position, I could see the rise in water level in that particular standpipe only up to this much. Why the water is getting raised only up to this much? Why not till here? Why is that water is not getting raised till here? Because there is a head loss existing when the flow is taking place through the soil sample, and that head loss, what is existing when the flow is happening through the soil sample, is what we have indicated as H. Okay, so automatically how much is my pressure head corresponding to the position of point B? What will be the rise in water level when the standpipe is inserted at point B position? So water would rise in the standpipe only till this much height, and that height is nothing but is what I can write it as. Okay, don't exactly understand this to be existing at some height here. Okay, I'm sorry, there is a mistake. Water will not exactly rise till here. We don't know. Water might be rising till here, or water might be rising till here, or water might be rising till here only. It may not exactly rise only till as like what is indicated there. Water may not exactly rise till the position of the top of your soil sample. Please do understand. Okay. So the pressure head corresponding to point B position is what I can write it as H1 plus H2 minus H. Pressure head at point B, if there is no flow existing, then automatically the pressure head at point B is H1 plus H2. But because of the flow, what is taking place through the soil sample, there is a head loss. How much is that head loss? Small h is the head loss, as there is a flow happening through the soil sample. So if there is no flow happening, the total pressure head is H1 plus H2. And as there is a seepage happening through the soil sample, so automatically there is a head loss existing. So my total pressure head, in turn, let me say, pressure head existing at point B is nothing but H1 plus H2 minus H. So is what I can now come back to your expression where I was trying to deal with calculation of your pore water pressure at point B. So pore water pressure at point B is nothing but unit weight of water at point B. Sorry, unit weight of water, which is anyhow same at any point, into the corresponding pressure head. So corresponding pressure head is nothing but H1 plus H2 minus H, which gives me what is called as your pore water pressure at point B. Once we know what is the pore water pressure at point B, so the effective stress what we are trying to calculate at point B comes out to be the total stress at point B minus your pore water pressure at point B. So we know how much is my total stress at point B, how much is the pore water pressure at point B. So if I try to expand your terms and if I try to cancel some of those terms, what I'll have is, if you look at your total stress is gamma W into H1. Even in the pore water pressure also I have gamma W into H1 term. So both gets cancelled. And what I'll be remaining is with your gamma Sach into H2 minus gamma W into H2, and minus of minus becomes plus H or gamma H into gamma W into small h. So automatically the terms what will be remaining is gamma sach into H2 minus gamma W into H2 plus gamma W into small h is going to be my effective stress at point B. Now, if you look at this term and this term, H2 is common, and if I take H2 common, what I'll have inside is gamma sach minus gamma W, where saturated unit weight minus unit weight of water is what we'll be writing it as submerged unit weight into H2 plus gamma W into H. Okay, that becomes my effective stress at point B. So whatever I was trying to discuss, look at this expression for total stress, which we have already talked about, pore water pressure, which we have discussed, and the effective stress. Once we start calculating, this is how we'll be getting the effective stress at point B position. So effective stress at point B is nothing but H2 into submerged unit weight of the soil plus small h, that's head loss happening when the flow is taking place from point A to point B into corresponding unit weight of water. Okay, so that's how we calculate how much is the effective stress at point B. Now let's go ahead and seeing how to calculate your total stress at point C. Now, how do we calculate the total stress at point B? It's all because of the material which is there over and above the position of point C. So that's some part of the soil that is depth of Z meters, and over that you have H1 meter of water body. So total stress at point C is nothing but unit weight of water into the corresponding height of water body, that is H1, plus the soil is saturated. So the saturated unit weight of saturated unit weight of soil into the corresponding height of the soil strata. So that is nothing but Z meters. That is going to be my total stress at point C. And likewise, if I want to calculate the pore water pressure at point C, so how much is going to be my pore water pressure at point C? Now, water in that particular standpipe, which is inserted at point C, the water is getting raised up to some certain height in the standpipe. So my objective is to understand how much is that corresponding pressure head at point C. Now, if I want to understand how much is the pressure head at point C, first I'll try to blindly see from point C position, this height till here is Z plus H1. When the water is moving from point A to point C, what has happened? Some amount of head loss has happened. Now, what is that amount of head loss happened when the water particle has traveled from point A to point C? When the water particle has traveled from point A to point B, we said the head loss is small h. Okay, I repeat, when the water particle has traveled a distance from point A to point B, the head loss is small h. Now, in case if the water particle is traveling from a point A to point C, how much is the head loss? Okay. When the flow is taking place from point A to point B, that means the soil sample is traveling a distance of, water particle is traveling a distance of H2, where the subsequent head loss is small h. Now, I am not looking from point A to point B, rather I am looking from point A to point C only. That's nothing but the distance traveled is small z. When the water particle is traveling a distance of small z, the corresponding head loss which has happened, let me say it is something H1. Okay, so I want to calculate how much is this H1 value. So that H1 value, if I am trying to calculate, we can cross multiply these terms and equate them. So if I try to do that, H2 into small h1 is equal to z into small h. So from this I can say your so-called small h1 that I am trying to calculate comes out to be z by h2 into small h. And what is this z by h2 if I just want to understand? So this z by h2, oh sorry, not z by h2, rather I should be just small h by capital H2. Small h by capital H2 is nothing but it is what I can write it as your hydraulic gradient. Why is that I can write it as hydraulic gradient? Because small h refers to that of your total head loss for a total length of seepage through the soil sample, which is nothing but H2. Okay, so small h by capital H2 is simply nothing but is what we can write it as your hydraulic gradient. So in the process, I can also rewrite my term that is small h1. Okay, small h1 is nothing but z into hydraulic gradient. So from here only, the earlier expression only, I am trying to write down that so-called small h1, which I am referring it as the head loss that happened from this point to this point. I repeat, this is the head loss that I am referring it as h1. Okay, and that h1 value is nothing but it is equal to your z into the I value, where I refers to that of the hydraulic gradient corresponding to the flow condition of the soil sample. So once I understand what is my pressure head or head loss corresponding to the point C position, then automatically my pressure head value corresponding to point C is what I can write it as. Okay, right. So the pressure head corresponding to this point C position is what I can write it as this much head minus this much head loss. Whereas this much head, what we are looking at is nothing but it is equal to Z plus H1 minus the head loss what took place because of the water particle traveled from point A to point C, which is H1. Pressure head corresponding to point C position is nothing but it is equal to H1 plus Z minus small h1. This is going to be my pressure head corresponding to your point C. Once I know the pressure head corresponding to point C, then the pore water pressure corresponding to point C is nothing but unit weight of water into the pressure head at point C. So pressure head at point C is nothing but h1 plus z minus small h1. So I understood what is my total stress at point C. I understood what is my pore water pressure at point C. Then the effective stress is what I can calculate as your total stress minus pore water pressure. So in that sense, I can simply write down what is that I am trying to look at according to what we have discussed. And if I try to calculate that, I'll be getting my expression for effective stress coming out to be what I could see here. As like what I have told you earlier. So this term and this first term gets cancelled, and what I'll have is gamma sach into Z minus gamma W into Z, which I can write it as Z if I take it common. That's nothing but gamma submerged into Z, and minus of minus becomes plus, and gamma W into small h1, where small h1 is nothing but Z into I, where I we are calling it as your hydraulic gradient, where that hydraulic gradient value is equal to small h by capital H2, which we have already seen and discussed how to calculate that. And that's how my expression comes out to be. So what we had earlier from the previous expression that we have seen is Z into submerged unit weight of the soil plus, we said it's nothing but gamma W into H1, small h1, where that small h1 we calculated it as I into Z. Okay, so which is that we are getting that as your effective stress at point C. So we have seen either at the top of the soil sample or either at the bottom of the soil sample, or in the other way I can call it as at the upstream end of your soil sample or at the downstream end of your soil sample or anywhere in between also, we are able to understand how to calculate your total stress, effective stress and pore water pressure that is existing in the soil. So wherever you wanted to calculate your total stress, pore water pressure and effective stress in the soil sample, then I can try to understand as at the top of the soil sample, you know what is your total stress. At somewhere in between, you know total stress. At the bottom of the soil sample also, you know the total stress. Then I can go ahead in understanding how is your total stress varying with the depth, and how is your pore water pressure varying with the depth, and similarly how is your effective stress varying with the depth. All the data that I have calculated from the top of your water surface, if I am trying to consider it as your 0th elevation, then at bottom of the water table, that means at the top of the soil sample, how much is my total stress, how much is the pore water pressure, how much is your effective stress. If all those data points are plotted in the form of a graph, then you'll be getting this much is my total stress at point A, this much is my total stress at point C, this much is my total stress at point B. If I join all these points, then I can simply get a straight line, and it's not a continuous straight line. So from this point to this point, it's a straight line with some slope. From this point to this point, it is another straight line with some other slope. Because why I'm saying some other slope? because the profile of the material is not same. Above it is the water body only, below it is soil. Okay, so automatically the profile of your soil as it is getting changed, then obviously these expressions what you are coming across with are also having the variation. So the slope of that particular equation what you had here and the slope of the equation what you had here is going to be different. As the slope is different, slope of this line is different, so automatically from here to here it could have some slope, another straight line, but from here to here once again it is a straight line, but thing is that it could be with some other slope. And likewise, that's how your total stress is varying with the depth, as you have already calculated how much is the total stress at different points in the soil sample, and that's how you can try to plot that. And similarly, we have also seen how to calculate your pore water pressure in the soil sample at different depths. So the pore water pressure, if I'm plotting it, I'll be getting a line like this. And similarly, this indicates me how is your effective stress varying with the depth, all those points if you try to understand. So I can clearly know that your effective stress is varying with the depth, and this is how your effective stress is varying with the depth. At top of the water body, effective stress is 0. Even at the top of the soil sample also, your effective stress is 0. So automatically I can say effective stress varies from 0 to 0. It means it coincides with this vertical axis. And from this point to this point, the effective stress is varying as a linear function. And at point C, we know how much is our effective stress. If I can plot that point, so from here to here by means of a straight line, I can join this point. And once again at point B, we know how much is our effective stress. So once we know how much is the effective stress at point B, so from this point to this point, we can try to join these values by means of a straight line. Okay, so that's how we can try to plot. That's how we can understand how is your total stress varying with the depth, pore water pressure varying with the depth, effective stress varying with the depth. Not just only in the case when there is no seepage happening, even in the cases when there is a seepage happening. And particularly this case of seepage, what we have seen is a downward seepage. Okay, so just try to have an understanding of how much is my effective stress at point B when there is a downward seepage happening, and later on when there is an upward seepage happening, how much is the effective stress that is existing at point B we'll be looking at. And from that I'll try to talk about some term which is very important for us to know when there is an upward flow taking place through the soil sample. Why is that we say upward flow is going to be a critical flow in the soil? We'll try to understand that. Next, let us see how to calculate the stresses in the saturated soil when there is an upward seepage happening. So how can I say there is an upward seepage happening in this particular case means, okay, let's say the pressure head corresponding to this particular point B has got some water body which gives you the pressure head existing in the standpipe raising till here. Okay, so this much pressure head, once we say, it's nothing but from point B the water is getting raised up to the so much reference height in the standpipe. So this height is what we can simply write it as H1 plus H2 plus small h is what is indicated additionally over and above the water table position. That's my pressure head at point B. And if you look at how much is my pressure head corresponding to the position of point A, so the water gets raised only till the water level that is available on the position above your point A. So that's nothing but we are calling it as your H1 height. So the pressure head corresponding to point A is simply nothing but it is H1. So because of that total head difference between upstream, which I am calling it as point B. Why I am calling your point B as your upstream? Because if I start calculating my what is called as your total head at point B, so total head at point B is nothing but elevation head at point B. So if I choose this itself as my reference datum, so from the reference datum, the elevation head of point B is 0 plus the pressure head corresponding to the position of point B is nothing but H1 plus H2 minus small h is what I understand by looking at your standpipe, the rise of water level in that particular standpipe. And that gives me what is my total head at point B. Let me calculate how much is my total head at point A. So total head at point A is nothing but elevation head of point A. So the point A is at a height of H2 from the chosen reference datum plus what is the rise in water level when the standpipe is inserted at point A? That's nothing but the pressure head at point A is nothing but it is H1. So total head at point B is higher when compared to that of the total head at point A. So because of which the flow is going to happen from point B to point A. And once there is a flow happening from point B to point A, then what are the issues that we are going to be encountering? Let us try to understand after talking about how what are the total stresses at different points in the soil sample, pore water pressures at different points in the soil sample, and effective stresses that are getting developed at different points in the soil sample. Now, how much is going to be my total stress at point A in the soil sample? Total stress is always because of your weight of the material or mass of the material existing over and above that particular point. So which is that material existing above point A? So it's only the water body. So the total stress at point A is nothing but it is unit weight of water body into the corresponding height of that water body existing above point A. So it's simply nothing but gamma W into H1 is your total stress at point A position. And next, pore water pressure at point A. So pore water pressure at point A is also nothing but gamma W into H1, because when the standpipe is inserted at the position of point A, the water is getting raised in that standpipe only up to a height of H1 meters. So automatically the pressure head at point A is H1, and your pore water pressure corresponding to the point A position is nothing but gamma W into H1. So total stress at point A is known, pore water pressure at point A is known, effective stress if I am trying to calculate, so which is nothing but total stress at point A minus pore water pressure at point A, gamma W into H1 minus gamma W into H1, which simply comes out to be 0. The effective stress at point A is coming out to be 0. Even earlier also at point A, the effective stress was 0. Now also at point A, the effective stress is 0, because over and above that particular point, you don't have any solid content existing. So stress carried by non-existing solid particles is obviously 0. Next, moving on to the next case, that is how much is my total stress, pore water pressure and effective stress corresponding to point B position. If I want to calculate how much is my total stress, pore water pressure and effective stress corresponding to point B position, that I can try to do by writing it here. Let's say my total stress at point B is equal to, because of all the material existing above your point B position. I repeat, because of, I am trying to talk because of the self weight of the material, right? So whatever is the material existing above your point B position. So that's H2 height of soil strata, which is saturated soil strata, and above which H1 depth of water body. So the total stress at point B position is nothing but, I can write it as, so it is gamma W into H1 plus gamma sat into H2 is going to be my total stress at point B position. Similarly, if I want to write down my pore water pressure at point B, pore water pressure corresponding to point B position is nothing but unit weight of water into the corresponding pressure head existing at point B. Already we have seen the amount of pressure head at point B is nothing but H1 plus H2 plus small h. Okay, so that gives me how much is my pore water pressure at point B. Then automatically, if I know what is my total stress at point B and pore water pressure at point B, then the effective stress at point B is nothing but total stress at point B minus pore water pressure corresponding to the position of point B. If I try to expand those terms, what I'll have is gamma W into H1 minus gamma W into H1 gets cancelled. Gamma sats into H2 minus gamma W into H2, which I can write it as gamma submerged into H2 minus gamma W into small h. Okay. Now, the effective stress, what I am trying to calculate at point B is coming out to be what is nothing but gamma submerged into H2 minus gamma W into small h. Okay. And if you look at the previous case where we have calculated the effective stress at point B for the downward seepage flow, you could understand the expression. Let me go back to that particular expression, what I was particularly talking about. Yeah, the effective stress, what you had here, just look at here. It's nothing but H2 into gamma dash. Here, gamma dash generally refers to what is called as submerged unit weight. Submerged unit weight need not be always written as gamma sub. Okay, so submerged unit weight will also be represented as gamma dash. Wherever you see gamma dash is nothing but it is the submerged unit weight of the soil. Understand that. So even in the case of your downward seepage, in the case of the downward seepage, the effective stress at point B, what we had is H2 into submerged unit weight plus small h into gamma W. And when it comes to the case of your upward seepage, so when it comes to the case of your upward seepage, the effective stress at point B is nothing but it is H2 into submerged unit weight minus small h into gamma W. So what is happening when there is a downward flow, when there is an upward flow with respect to the point B position? This particular point is very critical for us to understand. So when there is a downward seepage taking place, for downward seepage case, the effective stress at point B that we had as H2 into gamma submerged plus small h into gamma W. But in the case of your upward seepage, okay, so that means in this case, this is your upward seepage case. What I can understand is that effective stress developed at point B is decreasing. For a downward seepage case, the effective stress developed at point B was increasing. Why is it was increasing? Because of this additional term, the effective stress value was increasing. But here in this case of upward seepage, because of this term, as it is a negative quantity, so there is a decrease in your effective stress value. And because of this decrease in the effective stress value, the subsequent strength of that particular soil, what you are calculating at the point B, where the seepage or the flow is entering into the soil sample in the upward direction. As the flow is entering in the upward direction into the soil sample, the strength of the soil is decreasing. As the strength of the soil is decreasing, your so-called water particle, what is trying to seep through your soil sample due to the flow taking place, that water particle will certainly try to even carry away your solid particles existing in the soil sample. And in the process, when the water particle, due to the excess pressure, when it is trying to carry away your water particle along with the, when the water particle which is trying to seep through the soil sample in the upward direction, due to that decrease in strength of the solid particle contact, so solid particles also will be getting lifted in the upward direction. And after some point of time, because of this continuous phenomena, what we'll see is that particles are no more going to be stable in its position at the soil sample at where the water is entering in, so in the upper direction. So water particles will start slowly carrying away the solid particles also through the interconnected void path. And at some point of time, you'll see the strength of the soil starts continuously decreasing, and which results in the failure of the soil. So this upward movement of your solid particles along with the water particle is something very critical for us to understand in order to know how is the condition of the soil, or how will be the condition of a structure which is going to be constructed on that particular soil strata when there is an upward seepage taking place in the soil. If there is a downward seepage taking place through the soil, it is not going to be very critical for us, but when there is an upward seepage happening through the soil sample, it is going to be relatively very critical, where the strength of the soil is going to be decreasing as the seepage progresses, and as the strength decreases, automatically the structure is no more going to be very much stable when there is an upward seepage happening through the soil sample. So that's the reason why whenever you encounter the cases of an upward seepage expected to happen, we try to provide what is called as a proper concreting basement, so that your weight of the concrete base is going to be high, so that the pressures being exerted from the bottom on the structure can be minimized. Because if the weight of the self weight of the structure is going to be more when compared to that of the pressures which are being exerted from the bottom on the structure due to the seepage, so automatically then what happens is your structure is going to be stable. In case from the bottom of the structure, the pressures due to the seepage on the bottom of the structure is more when compared to the self weight of this particular structure, then what is going to happen is, as the self weight is relatively less when compared to that of this seepage pressure, automatically the resultant force is going to be in the upward direction, and the structure starts getting lifted in the upward direction because of that excess seepage what is taking place. Okay, so you have to be very careful in designing the structures. Before you start designing any particular structure, we have to understand whether the flow is happening in the upward direction at the bottom of the structure, or whether the flow is happening only in the downward direction. So depending on that, we have to take the necessary precautionary measures in understanding or in minimizing that so-called seepage pressures, which are going to cause the failure in the structure. Okay, so how to minimize the seepage pressure and all that we can try to understand in later courses or in less subsequent courses. So we'll try to see, maybe by solving one or two problems in later stages, we'll try to see how we can minimize your so-called seepage pressures. That's nothing but the pore water pressure which is trying to cause an effect in lifting your structure. And similarly, not that only at point A and point B, even at point C also, if I want to calculate, I can subsequently go ahead in calculating my effective stress value at point C position, as like we have done earlier in the downward seepage case. I can see how to calculate the total stress, pore water pressure, and effective stress. So I expect you to go through it and take some time in solving it. How to calculate your different stresses at point C. Once we understand your different stresses at point C, then we can go ahead in plotting how is your total stress varying with the depth, how is your pore water pressure varying with the depth in the soil sample, and how is your effective stress is varying with the depth in the soil sample. That's what I was referring to. Okay, so now whenever we are looking at a case that is stresses in the saturated soil for an upward seepage condition, so we try to come across with some critical case in the sense, as I told you earlier, when the effect of your sulfate of the material which is acting in the downward direction, if it is balanced by the effect of your that seepage pressure additionally coming into picture. Okay, so the effective strength of the soil automatically reduces, and at some point of time it becomes zero. And once the effective strength of that particular soil becomes zero, or the effective stresses developed in the soil becomes zero, then solid particle to solid particle interaction decreases, and the resistance between the moment of one solid particle to the other solid particle decreases, and results in what is called as dispersion between one solid particle to the other solid particle, indicating that the relative strength between the particles is almost zero. And once the relative strength of these solid particles is almost zero in the existing soil medium, then soil will almost behave like a liquid material. Why the soil is behaving like a liquid material? Because the effective stress developed in the soil is becoming zero at that point. If the effective stress developed in the soil is zero, then there is no forces being carried by the solid particle. So automatically we say it is as similar to that of the behavior of your water. The effective strength of the water is nothing but it is zero. And once the solids behaves like a liquid material, then automatically what we see is, due to the continuous seepage happening, so your solid particles also gets carried away with your water particle, and you will not see any more solid particles stable existing there in its position. So you are going to see the failure taking place. That's what is mentioned here. So at any depth Z, Z into gamma sub indicates you what is called as your submerged weight of the soil. This in turn refers to that of the submerged condition of the soil. So it's a pressure corresponding to the submerged soil which is acting in the downward direction. And when it comes to your second term is nothing but I into Z into gamma W, refers to that of what is called as your seepage pressure which is acting in the upper direction on that solid particle. So which we call it as your, this is nothing but it is the seepage pressure. And whereas this Z into gamma W is nothing but the pressure exerted because of the submerged condition of the soil in the downward direction. Okay, so in the downward direction, the so-called existing pressure on the soil medium at point B or at any particular depth is Z into gamma sub. In the upward direction, it's nothing but I into Z into gamma W. So whenever you are I into Z into gamma W, which we are calling it as seepage pressure, when it gets balanced with the submerged pressure, then automatically the so-called effective stress, what you are trying to calculate, comes out to be equal to 0. So the effective stress, what we calculate at any depth, it need not be at point C. At any depth, it could be at point B or at any other point. So because of that flow happening through the soil sample, so that effective stress reduces to 0. And once that effective stress reduces to 0, then automatically we say the soil is no more going to be behave like a soil medium, rather it behaves like a liquid material. So once that so-called solid particles, which are relatively losing its strength, and where the effective strength of that solid and soil medium is becoming 0, then what we call that particular condition as sand boiling condition. What does this sand boiling means? So why do we call this particular as sand boiling? Why not clay boiling? I'm particularly talking only about sand boiling. I'm not talking about your clay boiling. Why? Because this effect of decrease in effective strength and becoming 0 happens only in the case of your sand particles. Why? Because only in the sand particles, as the so-called contact between particle to particle, that so-called resistance or frictional resistance in the other way I can call it as. So as that contact is getting decreased, automatically the strength of that particular sandy particles is becoming 0, and particles will start getting dispersed. They relatively move away from each other, indicating that the strength of the soil has almost becoming 0. Almost becomes 0. And whereas in the case of clay, though this same phenomena is, let's say if I am understanding the similar kind of phenomena is what I am trying to look in the case of clay. But in the case of clay, what happens is one clay particle is strongly bonded with the other clay particle because of what is called as the cohesive nature. Okay, that so-called force of attraction between two clay particles relatively holds your clay particles together. That's the reason why we don't call this phenomena of effective stress becoming 0 in the case of your clay particles. We talk in the case of only your sand particles. Okay, so that's the reason why. Now, why are we calling it as boiling? When you look at water, when the water gets boiled, what do we see? Air bubbles starts coming up in the upper direction. In the similar way, here also, as the seepage pressure is balancing your submerged weight condition of the soil, then automatically, due to that excess seepage pressure, your solid particles also will be getting lifted in the upper direction, as similar to that of your bubbles. What we see when you try to boil your water. So that's the reason why we call this particular phenomena where the effective stress developed in the soil is becoming 0. So this particular phenomena is what we call it as your sand boiling condition. Okay. So whenever your effective stress developed in the soil sample is becoming 0, we say that corresponding hydraulic gradient where your effective stress is becoming 0 is what we call it as your critical hydraulic gradient. Why do we call it as critical hydraulic gradient? It is that particular hydraulic gradient where the effective stress developed in the soil is becoming 0. So that corresponding hydraulic gradient is what we call it as your critical hydraulic gradient. And how do we calculate that critical hydraulic gradient? So if I can equate this effective stress expression to 0, and if that effective stress expression is equated to 0, then I can try to rearrange your terms, because on both the left side and right side terms, Z gets cancelled out. And what I'll have is gamma sub is equal to I critical into gamma W, where that I critical is nothing but is what we can write it as here gamma sub by gamma W. Okay, so your critical hydraulic gradient, okay, ICR is what I have told you as nothing but critical hydraulic gradient. Why do we call it as critical hydraulic gradient? It is that hydraulic gradient where your so-called effective stress developed in the soil is becoming 0, and because of that effective stress, what is becoming 0, the soil, what is supposed to be stable, is no more going to be stable. Rather, you see the particles coming out of the soil sample because of the upward seepage. Sir, why is this phenomenon not happening in the downward seepage? Because when the seepage is happening in the downward direction, obviously the submerged weight of the soil is acting in the downward direction, and the seepage pressure is also acting in the downward direction, which is not causing your effective stress in any condition to become 0. But whereas in the case when there is an upward seepage happening, then in such case the submerged unit weight or submerged weight condition of the soil is in the downward direction, seepage pressure is acting in the upward direction, automatically resulting in a situation where the effective stress is becoming zero under particular hydraulic gradient condition, which we are calling it as your critical hydraulic gradient, where this critical hydraulic gradient is defined as the ratio of submerged unit weight of the soil by unit weight of water. In some cases, people also will be writing it as submerged unit weight is nothing but saturated unit weight minus gamma W by gamma W. So if I try to separate gamma sat by gamma W minus 1 is what I can also even write it as, and accordingly you can define your critical hydraulic gradient. So the same critical hydraulic gradient, if you can look back into your expressions, what we have talked about, saturated unit weight expression, if you can recall, okay, saturated unit weight is something what we can also even write it as GS plus E by 1 plus E into gamma W. If you can recall from your first unit, that is saturated unit weight in terms of specific gravity and void ratio, if I am going to be writing down. So I can write down my saturated unit weight as GS plus E by 1 plus E into gamma W. So in this particular expression, what I have represented for critical hydraulic gradient, I can replace your saturated unit weight as GS plus E by 1 plus E into gamma W minus gamma W by gamma W. If I am going to write all this particular story and rewrite everything, look at here, I am just doing it. GS plus E by 1 plus E into gamma W minus gamma W, this total divided by gamma W. So I can take gamma W common from numerator and denominator and I can cancel it out. So what I'll have ultimately is GS plus E by 1 plus E minus 1. And if I rearrange your terms to get what is my critical hydraulic gradient, then the critical hydraulic gradient comes out to be GS plus E minus of 1 plus E by total 1 plus E. And if I expand it, what do I get? Plus E minus E gets cancelled. So automatically my critical hydraulic gradient comes out to be GS minus 1 by 1 plus E. So I can define my critical hydraulic gradient if the data is known in terms of specific gravity of soil solids and void ratio of the soil. So I can calculate the critical hydraulic gradient value for that particular soil. Or otherwise, if I know the saturated unit weight and automatically, then I can also even try to calculate what will be my critical hydraulic gradient value for that particular soil. Okay. So whenever your soil reaches to a case where the effective stress developed in the soil for an upward seepage flow condition, where the effective stress developed in the soil is nothing but it is equal to 0. Once the effective stress developed in the soil is becoming 0, then the strength of the soil is becoming 0. And for that strength of the soil condition where it is becoming 0, you will see that your particles will start getting lifted in the upward direction because of the seepage taking place through the soil. And this results into a phenomena, the failure. Subsequently, what is happening there is what is called as quicksand condition, or otherwise we also call it as sand boiling. I repeat, this same phenomena, what I am trying to talk about as sand boiling, is otherwise also called as quicksand condition. Okay, we'll stop our discussion for today here, and we'll continue our discussion in our next class.